A couple of videos ago, Dr. Kataron had asked us to identify an unknown plant from planet Samudra. We had determined that plant height and plant color were features we wanted to use, and plant name was our label. Now, something I had mentioned in the last video is that we can represent our features as column vectors. So the first row of the dataset can be represented as x1 equals 5 centimeters green, where the first row in our vector would represent plant height and the second row would represent plant color. Unfortunately, while plant height is a number, plant color is not, so the computer won't be able to understand this. After all, vectors can only be composed of numbers. Knowing that the plants on planet Samudra are only green, blue, and red based on our dataset, can we perhaps map the colors to numbers? Maybe green maps to 1, red maps to 2, blue maps to 3. So x1 equals phi 1, and x2, which is the second row corresponding to Whisper Lotus, is 102. Not quite. See, 2 greater than 1 signifies to the computer that red is greater than green. Also, if blue is assigned 3, it signifies to the computer that the blue is closer to red than it is to green. That just doesn't make sense. Clearly, while plant height can be compared numerically, that is, you can tell if something is a taller plant or a shorter plant, you can't do the same with plant color. That's because plant color is a categorical variable. Blue, red, and green are different categories. So what's the solution? Feel free to pause the video if you want to think about it a bit. Continuing on, computers understand zeros and ones well. How about for plant color, we use indicator or dummy variables that represent the existence or lack of that color. For example, if we have a 3D vector, each entry in the vector corresponds to green, red, or blue. 0 if it's not that color, 1 if it is. So for example, a green plant is represented by 1, 0, 0. A red plant is represented by 0, 1, 0. A blue plant is represented by 0, 0, 1. This would totally work since each of the vectors are equidistant to one another. What we call this is one-hot vectors. Vectors that are hot like Miss Paws. Gosh, someone turn the AC around here. Okay, so let's pull it all together for the first entry in our dataset corresponding to lumen kelp. Instead of 5 centimeters green, we're going to first drop the centimeters in the first entry because we know that the computer won't understand that. Also, all the plant heights are in the same unit, so we can just keep the phi and not worry about units. Keep in mind that when we do try to make a prediction of what kind of plant our unknown plant is, we need to be consistent and make sure that the plant height is in centimeters. Now, instead of green, we're going to switch it to the vector that we said we would represent as a green plant, 1, 0, 0. Putting it all together, the vector would be 5, 1, 0, 0, a 4-dimensional vector where the first entry represents plant height and the last 3 entries represent plant color. Keep in mind though that the computer just takes in these vectors. It has no idea what each entry in the vector represents. By the way, this is why in my last video I had said that the number of dimensions we deal with is closely related to the number of features that we're working with, but not necessarily the same. For 2 features, we end up with a 4-dimensional vector. So keep in mind that if you're working with a real-world dataset with a ton more columns and especially categorical columns where there are lots of categories and not just 3, like we had for this problem with red, green, and blue, the dimension of our feature vector can dramatically increase. Now, I don't know about you, but I can barely visualize 3D, forget about hundreds or thousands of dimensions. You can see why this can and does pose a challenge for interpretability, a concept that we've discussed before, remember? The idea that we can easily understand why the AI model took certain decisions. If the model is working in a multi-dimensional space that we cannot visualize, it sure does make it harder for us to explain why the machine learning model took certain decisions. There are some promising solutions to make these models more interpretable, but we'll save those for a future module. Just to get a little more practice, let's create the feature vector for the second row in our dataset. Instead of 100 centimeters red, we instead have 100, 0, 1, 0. You can convert the other 2 on your own for some more practice. and that's pretty much it. And you'll tell me that's cool and all, Miss Paws, but what if this planet had more than just 3 colors? What if they had light blue, dark blue, turquoise, cyan, indigo, teal, chartreuse, vermilion? Okay, I get it. You can stop right there before I start pretending I know what some of these colors even are. I get your point though. What if it's not a limited number of discrete colors? What if it's more continuous? What if we have different shades of colors? Well, if we had several colors and we want to be as specific as possible, we could use the RGB color system, for example. If you Google color picker, you can see the RGB values. Each color is represented as the intensity of its red, green, and blue components. Specifically, each component takes on a value from 0 to 255. So if we take a fancy color like teal, our red component is 0, our green component is 128, and our blue component is 128. Essentially, it's a color that is a mixture of green and blue. So what we could do is create a column vector as follows: 0, 128, 128, where the first entry represents red, the second entry represents green, and the third entry represents blue. Now, you might ask, but hey, in our previous example, didn't we take green as the first entry, red as the second entry, and blue as our third entry? The answer is the order doesn't matter, because again, the computer doesn't know what each of these entries mean. But you must make sure that your entry order is consistent between all rows in your dataset. So if red corresponds to the first entry for the first row in your dataset, it should correspond to the first entry for all other rows in your dataset, and so on and so forth. By the way, our one-hot vectors are not too different from this new way of defining our colors. Watch this. If our first entry is red, our second entry is green, and our third entry is blue, in the RGB color system, our vector would be 255, 0, 0. If we're consistent with entry orders and we're talking about planet Samudra with only 3 colors, our one-hot vector would be 1, 0, 0, correct? Let's do the same for green. In the RGB color system, our vector would be 0, 255, 0. On planet Samudra, our one-hot vector would be 0, 1, 0. And for blue, RGB would be 0, 0, 255, and on planet Samudra, 0, 0, 1. They are both very similar. The only difference is that our one-hot vector is a normalized version of the RGB vector. And in theory, if we are going to work with different shades of colors and not just RGB, we would only have to normalize our vectors so we're not working with very large numbers, such as 255. Okay, what is normalization? Well, you'll have to wait till the next video to learn more. See you soon! Want to go deeper into AI? Check out the MetaPlus certification program. Details in the description. Don't procrastinate!
ME to the HTA plus, that's my zone. Leaping hurdles, breaking boundaries, never alone. Miss Paws on the block.